Hello and welcome to our video about Commandino's theorem. To acknowledge Dr. Akbar for inspiring us to make this video. We made it for our geometry class, Geometry 3321 at UTD. My name is Brett Stafford, and the other two people that helped make the video are Jacob Rubine and Jesse Ortiz.
So about the history of Commandino. He was born in Urbino, Italy in 1506. He was most well known for translating the works of ancient Greek mathematicians, such as Archimedes and Euclid, so he had a strong knowledge of Euclidean geometry. He did publish original work, like in 1955, about the centers of gravity of solid bodies, and it is important because in that work he did discuss what we know as Commandino's theorem.
Alright, so let's go ahead and first state Commandino's theorem, which says the four medians of a tetrahedron are concurrent at point S, which divides them in a 3-to-1 ratio. We can see that on the image to the right, that on point S, the medians are concurrent. So first of all, what exactly is a tetrahedron? Well, a tetrahedron, or a triangular pyramid, is a three-dimensional solid shape composed of four triangular faces and four vertex. But also, what is concurrency? Let's talk about it. Concurrency of a shape is the intersection of three or more lines, vectors, or planes. Here on the image to the right, point S is the point of concurrency. You may already be familiar with similar shapes to the tetrahedron, such as the Egyptian pyramids, but those are actually square pyramids, not triangular. However, it's good to know there are different types of tetrahedrons, such as equilateral tetrahedrons, where the properties such as the faces and vertices are congruent and symmetrical, or irregular tetrahedrons. So before we start, let's talk about what we will need to know before we get into the proof. First, we'll talk about vectors. A vector v from point A to point B is an object that notes a direction and magnitude, or the distance, between those points. It is represented by an arrow above and as x, y, and z. Here we have point A and point B. Let's go ahead and connect point A to point B. This will be our vector v, and since it's a vector, we have a little arrow on top. We'll also need to know what is vector addition in this proof, but how exactly do we add vectors? Let's go ahead and take our vector u and our vector v, where u is equal to 1, 2, and our vector v is equal to 4, 3. To add these, we simply add the terms they have similar together, which are their x and their y's. So we will go ahead and add 1 plus 4, 2 plus 3, to get our vector w, which will be 5, 5. It's also important to know how scalar multiplication works for this proof. In scalar multiplication, we multiply a vector by a constant scalar, and this will change the vector's magnitude, but not the direction. Let's take vector u equal to 3, 5, and go ahead and multiply it by a scalar factor of 2. So we'll multiply 2 by each term inside the vector. So it'll be 3 times 2, and 5 times 6, equal to our new vector, 6, 10. Let's go ahead and call it v. This new vector effectively doubles the distance of our previous vector. We can go ahead and move on to Cartesian coordinates, which we are familiar with. Cartesian coordinates are a set of values or variables that help show the exact position of a point on a plane, such as x, y, and z. Each variable shows the amount of distance the point travels on its respective plane. Let's go ahead and have our x-axis here, our y-axis, and our z-axis. Let's go ahead and put a point here in the origin at 0, 0, 0. Let's go ahead and move it an x amount on the x-axis, and let's move it a y amount on the y-axis, and finally let's move it a z amount on the z-axis. Now we have our point here on x, y, and z.
Suppose we have vector A and some other vector, and we'll call it vector B. Okay? Now let's line them up so that we're moving B to the end of vector A, and then we'll connect those, so that will give us vector A plus vector B. Now if we do it in the opposite order, we go along vector B and then we go along vector A, that would take us to the same place that A plus B takes us to. So it doesn't matter which order you do it in. Okay, suppose we had 2 points, point A and point B, and let's see, point B and some point of reference called 0. Okay? Then we can represent the vector between 0 and A as vector A, and the vector between 0 and B as B. Okay, if we start at point 0 and add vector A and vector B, and then we also add negative vector A, that would bring us to point B. What is negative vector A? That's just vector A, but in the opposite direction. Okay? So if we start at point A and add vector B and negative vector A, that would bring us to point B. Okay? Through the vector B minus vector A. See, B minus A. So you subtract the vector that represents the point you start on from the vector that represents the point you end on, B minus A. Now suppose you wanted to go from point B to point A instead of from point A to point B. So you go in the opposite direction. Then you would just swap the order. It would be vector A minus vector B. And that's also because if you want to change the direction of a vector to the opposite direction, you just negate it or multiply it by -1. So we have what we had before with the points A, points B, vector A, vector B, and a vector from A to B is vector B minus vector A. But now what we want to do is we want to get the midpoint between 2 points. So let's just do the midpoint between some point A and some point B. So what you would do is you would start at point A and you would take this vector B minus A, but you would only go half the length of the vector. So if you want to go half the length, you could divide it by 2. So let's draw that out. B minus A over 2. And then let's say you want to find the point where that is. Well, you could start at 0 and then add vector A and then add B minus A over 2. So what is that? Well, let's try to work it out. So we have A plus B minus A all over 2. And then you can distribute that 1/2. And then you can group the A terms. And then you subtract 1/2 from 1. That gives you A over 2. And then you can factor out that 1/2. So it's vector A plus vector B over 2. So that is your vector that would take you to the midpoint between points A and point B. Let me define what a median of a triangle is. It's a line segment that connects a vertex of a triangle to the midpoint of the side that is opposite to that vertex. So here's what a median looks like, right? And you can do that to the other medians too. Okay? So each triangle has 3 medians, and they look something like this. You may have noticed that the medians appear to concur at some point inside the triangle. This is no coincidence. The medians of a triangle will always concur at a single point, which we will call the centroid. So let's draw that out. There's where the centroid would be, where they concur, and there it is. But how do we know that they concur? On this slide, I will attempt to prove that the medians concur. Let's draw the median from B plus C over 2 to A. Okay. Now, if we get the vector from B plus C over 2 to A, that is A minus B plus C over 2. So if we start at B plus C over 2, and then we add this vector, but we only do 1/3 of the vector. So we only go up the way 1/3 the way. And we can do that by adding B plus C over 2 to A minus B plus C over 2 over 3. So the B plus C over 2 just takes you to that point B plus C over 2, and the a minus b plus c over 2 all over 3 goes up the vector, but only 1/3 of the way up. And that simplifies to a over 3 plus b over 3 plus c over 3. You can see that because there's the a term has 1/3, the b term is 1/2 minus 1/6, which is 1/3, and similarly for the c term it's 1/2 minus 1/6, so that's also 1/3, right? Similarly, there's the point right there. The centroid, the alleged centroid, we're still proving it, right? Which is at a plus b plus c over 3. So if we have the other medians and we do the same thing except, from the other midpoint and do the other vector, it should still give us a plus b plus c over 3. And so it's actually on all the medians. This point is on all the medians. Thus, the medians concur at a plus b plus c all over 3. Okay, so now I'm going to define a median of a tetrahedron. Remember, there are also medians of triangles, but this is slightly different because it is for a tetrahedron. So if you want to construct a tetrahedron, first you need to have 4 points. Now 3 points makes a triangle. The 4th point, if assuming the 3 points make a triangle. If 3 points are all on the same line, they don't make a triangle. So assume they're not all on the same line. And then for the 4th point, it can't be inside that plane. So assume it's like somewhere up here or something. Okay? So then these 4 points could make a tetrahedron. Okay? Then each group of 3 points makes a triangle. Right? So there's one group of 3 points. Not all 4, just 3. And then for each triangle, we're going to also show the centroid of it. And we're going to color code it so that it has the same color as the opposite vertex. See, blue and blue. And then we're going to do that for the other triangles. Okay? So gray and gray. Right there. There's another triangle. And there's that centroid. And there should be one more. There it is. And then there's that centroid. Then the median of a tetrahedron is a line segment that connects a vertex on the tetrahedron to the centroid of the triangle that is opposite to that vertex. So for example, there's one median, there's another median, and there's the other, and there's the other. Okay. This means that every tetrahedron has 4 medians. Now remember that theorem we're talking about, which is Commandino's theorem, says that these medians concur. So I will let the next person, Jacob, try to prove that the medians concur for the tetrahedron. So basically he's just proving the theorem.
Now we will explore another proof to this theorem. First, let's generalize the problem. Rather than view a shape right now, we'll look into a set S of n points. From an arbitrary point P, we can establish vectors from P to each of the points in set S. If we take the mean of these vectors, we get a vector from a point P to the center of mass, the centroid. This is true regardless of the point P. If we include a point Q, we can add vector PQ to each vector VI to create the vectors UI. The mean of these vectors will also be equal to the mean of the vectors V plus the vector PQ, as shown in the proof right there. We can separate S into S prime and S double prime. S prime will be a subset of S with k points, and we'll take S double prime to be the complement, or the n minus k points that are not in S prime, which are basically all the points in S not in S prime. From there we can establish centroids, much as we would in S, as C prime and C double prime. From there the vectors from C prime to C will be equal to the vector from C to C double prime multiplied by the scalar n minus k over k. which means that C prime C also be equal to n minus k over n C prime C double prime, and that C double prime C will be equal to k over n C prime C double prime. Here's the proof. We establish S to be x1 to xn, S prime to be 1 to k, and S double prime to be the remaining xk plus 1 to xn. By subtracting the mean vectors, we can use the similar vectors for each of those means to use C prime C and C double prime C in terms of C prime C double prime. From there, we can get to this relationship and see that C prime C is equal to n minus k over k C prime C double prime. And it also shows that all 3 points fall on the same line, or also known as collinear. So how does this apply to shapes? Well, if we view triangles, and we can use their vertices for this arbitrary set S. We'll let S be the vertice xyz for a triangle, S prime to be xy, so the centroid will be the midpoint, as it is the center of mass between 2 points, being directly in the middle. S double prime will be the remaining point z. Clearly, the centroid will also be z, as it is the only point there. Now notice that if we draw C prime to C double prime, we get a median of the triangle. From that point, we could use that n is equal to 3 as x, y, z is 3 points, and k is equal to 2 as s prime is 2 points, to show that C prime C is equal to 1/2 C double prime. 1/2 of CZ. Finally, we can apply this to tetrahedrons. Well, let S be the 4 points W, X, Y, Z, the 4 vertices. Let S prime be this centroid of the lower triangle, which would make K be equal to 3. C prime will just be the centroid, right? And S prime will be the 3 vertices. S double prime will be W, and clearly C double prime will also be W. And if we follow the same formulas we use for the triangle, C double prime C will be equal to 1/3 of C double prime or CW, which would make it which is 1/4 of C prime W, or the median.
And here are our citations.